Hello all, welcome to this talk about the brief announcement with the title A Discrete and Continuous Study of the Max-Chain Formation Problem. I'm Jannik from the Heinz-Nixdorf Institute at Paderborn University, and this is joint work with Knollmann and Friedhelm Meyer of the Heide also from the Heinz-Nixdorf Institute, and Peter Kling of the University of Hamburg. We study a robot problem here, and in our model, the robots are simply points in the Euclidean plane. From the outside, they are indistinguishable, so every robot looks the same, and from the inside also, so there are no unique identifiers. The robots are completely disoriented, so they don't have any common coordinate systems. The coordinate systems of the robot can be arbitrarily inverted or rotated. The only thing robots agree on is unit distance. Beyond that, the robots cannot communicate, so they can't synchronize their views on the world. And robots only see a small portion of the world around themselves. They only see up to a distance of 1. And here we have a chain topology where we have inner robots and outer robots. Inner robots have 2 neighbors and outer robots only have 1 neighbor. And the distance between 2 neighbors in the chain is always at most 1. And the robots are oblivious, so they don't have any memory of the past. This is covered in the time model. We study 2 synchronized time models, the f-sync time model and the continuous time model. In the f-sync time model, we have fully synchronized look-compute move cycles. So robots observe their environment, compute target points, and move to these points. And this is synchronized among all robots in f-sync. And in the continuous time model, robots have continuous trajectories, can adjust their own speed continuously, while always having a speed of at most 1. So at every point in time, each robot has a velocity vector describing its movement with a bounded length. And now the goal is to take this initial chain and transform it into a straight line of length n-1. This is the largest possible distance we can achieve between the 2 outer robots. And now we have invented 2 strategies, one in the f-sync time model and one in the continuous time model. In the f-sync time model, we have the max go to the middle strategy, and intuitively it has to solve 2 tasks at the same time, to arrange robots on a straight line and to stretch this line. And therefore we have 2 roles in the chain for the alignment. Each inner robot executes go to the middle. This means every inner robot moves in every round to the midpoint between its neighbors. The outer robots stretch the chain as follows. They look at their direct neighbors and then assume that there's a virtual robot at distance 1 on the other side, and then they execute go to the middle with these 2 robots and jump away from their direct neighbor. This stretches the chain. And now I have a short video here for you. You can watch on YouTube, where you can see that this strategy somehow seems to converge to a straight line of length n-1. Unfortunately, there are configurations which do not converge to this line, and these are special cases of one-dimensional configurations. So a one-dimensional configuration is a configuration where all robots are already located on a straight line. Now we have 2 classes, marching configurations and opposed configurations. In marching configurations, the outer robots move into the same direction because the neighbors are in the same direction from themselves. And in opposed configurations, the outer robots move away from each other. And you might have guessed here, in marching configurations, this is somehow an undesired behavior because the robots move into the same direction. And for this, I have a video for you that this is indeed an undesired behavior and doesn't converge to the straight line we wanted to achieve. So summarizing, I can say as follows. We have 2 kinds of convergence for one-dimensional configurations, the convergence to a straight line of length n-1 for opposed configurations, and a convergence to a marching chain for marching configurations. And the runtime is in the order of n² log n divided by epsilon, and the upper bound where epsilon denotes how close we are to the final configuration because we only converge and never reach it really. And the lower bound is in the same order n² log 1 divided by epsilon. When we switch to 2-dimensional configurations, we identify a class of configurations which has a very high runtimes. These are these delta V configurations. And this parameter delta now describes the distance between the outer robots. And we can prove now that these configurations converge in time at least n² log 1 divided by delta to a straight line of length n-1. But if we choose delta now very small, we can get arbitrary high runtimes. So we conjecture that this is also an upper bound for two-dimensional configurations here, but so far we don't know it. But in the continuous time model, we actually could get rid of this dependence on delta. In the continuous time model, the first strategy one could think of is the following. Every inner robot moves with speed 1 along the angle bisector between its neighbors, so here. And as soon as it reaches the straight line between its neighbor, it moves with speed 1 to the midpoint, and then it follows the movements of the midpoints. The outer robots again move with full speed away from their direct neighbors, so with speed 1 away. And now we get the same behavior. We have marching configurations and opposed configurations converging to a marching chain or to a straight line of length n-1, but the runtime is faster. This is upper bounded by O of n. Yes, same for opposed. And the same class of configuration leads to a lower bound in two-dimensional configurations. Here we get a lower runtime bound of n times the logarithm of 1 divided by n times this angle. And this angle is essentially in the order of the delta we have seen before. So we essentially get the same runtime bound here. We only miss a factor of n here. And for this class of configurations, we could now identify that a crucial thing why the runtime is that slow is that the outer robots move with full speed. So with the following strategy, we can remove this dependence on delta. It works as follows. Outer robots do not move with full speed. They move only with speed 1 minus epsilon at every point in time. And this epsilon is a constant between 0 and 1. And this has two effects. In case of marching configurations, now the chain gathers because the inner robots are faster than the outer robots. And some of these marching configurations even get resolved. And in total, we get an upper runtime bound of O of n for a slightly different strategy as I have introduced here, but I don't have enough time now. So here we can see by reducing the speed of the outer robots, we can get rid of this dependency on the initial distance. And this is actually not possible in the absolute time model. And this concludes my talk now. I will be happy to answer questions in Slack.